Trigonometry, Chapter 6, Inverse Circular Functions and Trig Equations. Section 1, Inverse Circular Functions. Video 1, Summary of Inverse Functions, Algebra. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous chapter, we studied trigonometric identities. Excuse me. We both verified identities and used identities to evaluate trig functions. In this chapter, we will study inverse trig functions to a greater depth than when we experienced them previously. We'll also study more rigorous trig equations than the one we've seen previously. In this section, we study inverse trig functions. In this video, we review inverse trig functions algebraically. So no trig in this video. Now, when you have a function, y equals f of x, there are four main components we can consider. Number one, the domain of f of x, defined as the set of all real numbers x that make f of x both real, so no imaginary numbers, and defined, no zero denominators, amongst other things. Number two, the range of f of x is the set of all real numbers y, such that y equals f of x for some x in the domain of f of x. In other words, the values that can be outputs to the functions. Domains are inputs, range are outputs. Three, the action performed on the x that turns into the y. In other words, the formula. What is this function doing to the x to turn it into a y? Although technically that's not required to be a function, most of our functions actually perform some sort of action. And number four, the graph of y equals f of x, specifically the set of points of the form x comma y, where x is in the domain and y is the corresponding point in the range. Now, to discuss the idea of an inverse function, denoted f inverse of x with this little -1 here, we need to clarify what exactly we want this inverse function to do. For example, suppose we have f of x equals 3x plus 1, and we let x equals 5. Well, if we plug in 5, we'll get 3 times 5 plus 1, which is 16. So, since f of 5 equals 16, what should f inverse of x do? Well, we want the inverse function, typo here, we want the inverse function to undo what f of x did. And since f of x turned 5 into 16, we want f inverse of x to turn 16 back into 5. So we are saying if f of 5 equals 16, then we want f inverse of 16 to equal 5. In terms of inputs and outputs, we're saying that if f of x turns an input into an output, another typo, we want f inverse of x to turn that output back into the original input. This is like saying if a comma b is a point on the graph of y equals f of x, then we want b comma a to be a point on the graph of y equals f inverse of x. We want to undo what was done. Thus, the inverse of a function reverses the function's ordered pairs. That will be critical. Going back to the four main components of a function, what would it mean to reverse each ordered pair? In other words, switch the x's and the y's. Well, first it means inputs for one function would correspond to outputs of the other, because we're switching the role of the input and the output. And this implies that the domain of f of x, the things that go into one function, should equal the range of f inverse of x, the things that come out of the other function, and vice versa. Well, here's a visual to represent that. If we think of a set of numbers as an oval or an ellipse, so this red circle contains some numbers, and the blue circle or ellipse contains some other numbers, we can think of y equals f of x as being a function that takes an element from its domain and turns it into an element of its range. But f inverse of x would go backwards. So the domain of f of x, the one in red, what goes into the first function, turns it into something into its range, but that has to subsequently be in the domain of the inverse function so it can go back through and come out of the range in the range of the inverse function. So the domain of one function equals the range of the other. Now, what else does it mean to switch the x's and y's to change a function to its inverse function? Graphically, what happens when you switch an ordered pair's coordinates? Well, what follows is a graph of the function we saw earlier, f of x equals 3x plus 1, with 5 of its ordered pairs, and the same 5 ordered pairs plotted except with their coordinates reversed. The black line, which contains these 5 points, is the graph of f of x equals 3x plus 1. The green line down here contains the same 5 ordered pairs with their coordinates reversed, 1, 4, 4, 1, 2, 7, 7, 2, and the same thing for all 5 points on the black line. Now, the red dotted line is the graph of y equals x. That line is important because, do you see it? Every point on the black line was reflected across the red line. In other words, the point that was on the black line took its mirror image across that dotted line to land down here on the green line. Now, this implies that the graph of y equals f inverse of x is the reflection of the graph of y equals f of x across the line y equals x. In other words, if you have a function's graph and you want the graph of the inverse, you reflect it across that diagonal line. Or this way, I'm not sure how you're seeing it. But what about the function itself? If f of x equals 3x plus 1, then what function is f inverse of x? Now, to answer this, recall that the idea behind an inverse function is switching the x's and y's. Now, since the output of f of x, this function up here, is the y coordinate, saying f of x equals 3x plus 1 is essentially the same as saying y equals 3x plus 1. Switching the x and the y, which is the underlying premise of inverse functions, gives us 3y plus 1 equals x. But if the inverse function y equals f inverse of x is described by the equation 3y plus 1 equals x, it stands to reason that solving 3y plus 1 equals x for y should give us the inverse function. If you solve 3y plus 1 equals x for y, you get y equals x minus 1 over 3. So if f of x equals 3x plus 1, then f inverse of x equals x minus 1 over 3. It is straightforward to verify that the reversed ordered pairs on the graph will satisfy this function. In other words, for this function, these 5 ordered pairs will satisfy it, such as 16, 5. If I put 16 in here, 16 minus 1 is 15, divided by 3 is 5. Now, before we summarize all of this, there is an important thing to point out. Not all functions have inverse functions. For example, consider the simple function f of x equals x squared. Both 3, 9 and negative 3, 9 would belong to this function's graph, because when you square both 3 and negative 3, you get 9. As such, if we reverse them, the points 9, 3 and 9, negative 3 would belong to the graph of the inverse relation. A relation is like a function without the requirement that a function has. But no function can have both 9, 3 and 9, negative 3 on its graph. This would violate the vertical line test. No one input for a function can have more than one output. So how can we tell if a function has an inverse? Well, algebraically, we could ask if f of x is 1 to 1, which means 2 different x's always produce 2 different y's. Not the case with this function. In the case of this function, both 3 and negative 3, 2 different x's, produce the same y, 9, which is okay for a function, but not okay for its inverse. Besides, what would f inverse of 9 equal? 3 or negative 3? It can't be both. Functions don't do that. We can also check graphically to see if a function has an inverse. How? Well, recall that the graph of an inverse is the reflection of the graph of the original function across the diagonal line y equals x. If the inverse is a function, its graph will pass the vertical line test. So imagine reflecting across the diagonal and hit it with the vertical line. But if we reflect the graph back across the line, then that means the original graph would have to pass the horizontal line test to see if the inverse of the function is indeed a function. I think a visual would help here. Here's the graph of f of x equals x squared. It's a parabola, and there are the points negative 3, 9, and 3, 9. Notice the horizontal line y equals 9 intersects the graph at those 2 points. Now, if we reflect both the parabola and the horizontal line across that diagonal line, it looks like this. And now the horizontal line becomes a vertical line, which hits the graph of the reflected parabola twice, so it's not a function. So if we take it back here, Hitting it more than once with a horizontal line means that its reflection would hit more than once with a vertical line, meaning the inverse is not a function. This is precisely what I said. This suggests if a horizontal line crosses the original graph more than once, this one, then that original graph does not have an inverse function. It has an inverse relation, just not an inverse function. So let's summarize. If y equals f of x is 1 to 1, meaning its graph passes the horizontal line test, then there exists an inverse function y equals f inverse of x, in the sense that if a comma b belongs to the graph of y equals f of x, then the point b comma a belongs to the graph of y equals f inverse of x. This is equivalent to saying that the composition of the two functions is equal to x for all x in the correct domains. If they're inverses, then the domain of one is equal to the range of the other. That's because what comes out of one function has to be able to go into the next. Hence, one function's domain must match the other function's range. The graph of y equals f inverse of x is a reflection of the graph of y equals f of x across the line y equals x. Quick example, the black one is f of x equals x plus 3 quantity cubed, and its inverse is the cube root of x minus 3. Notice they are mirror images when you reflect them across the red line. And lastly, if f of x has an inverse, f inverse of x, we can find that inverse function by following the process. Change f of x to y, switch the x and y, solve for y, and then change y to f inverse of x. We saw that back here. We saw that it's almost there, right here, where we had replaced the function with y, switched the y and the x, solve for the y, and then replace the y with f inverse of x. So this is the fairly standard procedure for determining the inverse of a function when possible. There are some functions that have inverses, but step 3 is impossible. There's no now you try for this video.